planet.
Hi everyone, and welcome to another
The Earth is Flat on Planet Pluto,
an online live cosmic talk show about astronomy, science, and other stuff, where the guests are the clear highlight and where you can ask any questions and also participate by using the chat on this side on YouTube. Now, every Wednesday at 5:30 p.m. UK time, we'll try to bring you a cosmic topic and amazing guests who will share their passion for science and space. This is apparently already the 5th episode, but just like in all others, things can and will definitely go wrong. I must stress this all the time, and that this is obviously part of the scientific method. I mean, like blowing things up. And today we're even going to be talking about what happens when clusters merge, so it's even more appropriate. Obviously, it goes without saying, but when everything works perfectly, we never really learn anything. So it's fine if we stop hearing ourselves or if the image breaks, anything else. Now, during June and July, I'll be your host as we attempt to bring you lots of astronomy, science, experiences, the human side of looking up, and also a lot of fully random, but hopefully fun stuff. Like, for example, the sound of black holes merging in space. It's something random, but quite fun. My name is David Sobral, and I'm an astronomer and a scientist. And just like everyone else on this amazing yet insignificant planet, I'm 10% made of cosmos and 90% made of stars, which formed billions of years ago. Our home, the Milky Way, apparently is still socially distancing from Andromeda, which is great, but many galaxies do love to socialize and live in huge cities of galaxies, clusters of galaxies. Some of them contain up to thousands of galaxies, and they're really huge, like the largest structures in the universe. There are important questions we'll try to address today, such as what happens to galaxies in these cities? Do they look the same as our Milky Way? What happens when the cities of galaxies get attracted to one another and merge? Do they just blow up, or do they just pass through each other without much happening? How can we use machine learning to help us find and study these clusters of galaxies? Today's guests join us from the US, Portugal, and the UK, and they will tell us all about galaxy clusters and why they are so cool, but also so hot. And remember, you can participate and ask them questions live by using the chat here. And the voice from beyond, which you cannot see today, will collect your questions and we'll ask them to our guests. For now, though, please welcome our amazing guests that join us from all over the world. Andra Stroe from Harvard CfA in the US, and Afonso from the University of Lisbon in Portugal, and Matthew Chan from Lancaster University in the UK. Our audience is obviously ecstatic and looking forward to what you have to say. So thank you so much for coming into the show. I hope you're all doing well in different places in the world. And start with Andra, and just very briefly. So Andra is currently a Clay Fellow at the Harvard Center for Astrophysics. And Andra, you've been a fellow at the European Southern Observatory, or ESO, before. And you did your PhD in Leiden, where you've been studying all kinds of aspects related with clusters of galaxies, and also what happens when they merge and go bang. So perhaps the first question everyone would ask you is, what exactly is a cluster of galaxies?
Well, hello, everyone. Yeah, so that's an excellent question. Particularly in the nearby universe, we have a very good idea about what clusters are. So we think that in the early universe, there were some density fluctuations, and these density fluctuations grew with cosmic time into these cosmic megacities, the largest, densest structures in the universe, which we call galaxy clusters. So we think there are collections of thousands of galaxies clustering together. But there's a kicker. It's not only the galaxies, also in between the galaxies, there's a lot of gas, very hot ionized plasma, and also this mysterious dark matter, which actually contains most of the mass of the galaxy cluster.
So essentially the clusters, galaxy clusters are not just made of galaxies, right? So what dominates the, like, for example, the mass in a cluster?
Yeah, so in terms of luminous matter, actually most of even the luminous matter is in the form of this hot gas that's in between the galaxies. But actually most of the matter, about 90% of the mass in a galaxy cluster, is in the form of dark matter. So we don't really know exactly what dark matter is. It interacts gravitationally, so it has a gravitational pull. So this is how we can infer that it's there, but it doesn't emit any light, like optical light or X-ray light or radio light that we can directly detect with our instruments. So we can, let's say we only have some evidence for it existing from our other observations from galaxies and the hot gas, but not directly from dark matter.
And so I guess I see you're in space, very next to a cluster, and we'll probably explain a little bit more about what people can see. But apparently you can have one of these clusters, right? And because of gravitational interaction, they essentially attract and they can merge. So what does happen when they merge?
Yeah, so we know that the universe is highly non-uniform. It has a cosmic web structure. So you have a lot of these galaxy clusters located at the peaks, and then in between, you have all sorts of filaments that are connecting them. And once two of these galaxy clusters come close to each other, they can actually, because as you said, because of their mutual gravitational pull, they merge into each other. And you would originally think this is a very dramatic event, and it is. They're actually the most energetic event since the Big Bang, but the density is so small and all of these galaxies are so far away that actually what happens in many cases, they just pass through each other and then they come back again because of their mutual gravitational attraction. So it kind of goes like a pendulum until the two clusters settle into one.
So not a lot happens to the galaxies, but are there shock waves being generated? And
Yes.
are they real?
Yeah. So, you know, they do pass through each other, but they do feel that something is happening. So imagine that you have like two balls of gas, or let's say two balloons of water colliding with each other. In this case, you know, the gas kind of passes through each other a little easier than water would through water. But there are shock waves that are produced because of these two super fast moving balls of gas. You get shocks that travel through this medium and they actually accelerate particles to almost relativistic speed, so almost the speed of light. So very, very fast moving. So you have these shock waves that are moving at speeds of 2,500 kilometers per second. So, you know, there's some of probably the fastest moving objects we know of. So, you know, forget about cars or planes. These are much, much faster. And you actually also produce turbulence. So you have all of these turbulent eddies that are being produced in the intercluster medium because of the disturbance that's being caused by these two massive balls colliding with each other.
And right now, what kind of questions are you trying to address within these merging clusters?
So this is a topic that really it's a really big passion of mine. And I really try to look at galaxy clusters in a holistic way. So I'm trying to understand how, for example, this merger of clusters is affecting the galaxies within the cluster. So for example, are they going to form more stars or are they going to form fewer stars as the cluster is colliding? And I'm also trying to understand how these mergers are affecting all of this hot gas that's located in between to understand how much turbulence we can produce, how big are these shocks, and do the shocks as they go through the galaxies influence them in any way? Do they produce new stars? Do they maybe trigger some black hole activity at the center of the cluster of the galaxies? So, and in order to do this, you really need to look at all of these things together.
And we'll come back to that and learn even more about the exciting research you're doing. Anna, you're currently a postdoctoral fellow at Lisbon University after you spent some time in Germany, and you did your PhD at the University of Lisbon. I guess technically they're now exactly the same university, but you're not really at the same place. And you've been working on quite a lot of different things, including trying to understand the roles of nature and nurture for galaxies, both in and inside clusters, and also linking that to the way galaxies look like or their morphology. So based on the research that you've been doing, are galaxies really affected by the environment that they live in?
First of all, good afternoon or good morning or good night, everyone. Yes, like us that live in a village or cities and different countries, if you live in different planets or satellites, is up to you. But if you can be on Earth or the Moon or whatever, we are affected from our society, from our culture. Galaxies are affected from the environment they reside in. So yeah, they can look like very different, or the things could happen in different ways. If they have a very low neighborhood, they are almost isolated, or if they have a lot of galaxies nearby.
So in clusters, how do galaxies look like?
So inside the clusters, the galaxies look like baseball balls. They are like elliptical forms and very round and boring. But if you go a little bit away from the clusters, they typically look like a very spiral galaxies, super with arms and disks and a lot of things going on. So they are quite different. But yeah, inside the cluster, they are a little bit boring.
And specifically the galaxies, both in clusters and outside, do also their sizes, do they actually change, or is this just a shape? Are galaxies like bigger in clusters or smaller in clusters?
So that is a good question. So we have both. We have big galaxies inside the clusters and big galaxies outside the clusters. What happens is if you go inside the cluster, a big galaxy becomes bigger, and a small galaxy becomes smaller because it will start interacting with other galaxies, and it will lose gas and stars and starting being very smaller. And the bigger one that are interacting, pushing everything, are starting bigger, bigger, and bigger. So in terms of size, we can find both in and outside the clusters, but how it enters in the cluster can modify a lot the shape of the galaxy.
And for example, to study in your own research clusters and this kind of nature nurture dichotomy, what kind of telescopes did you use?
So I use a very large telescope. It's a ground-based telescope in Chile. As of now, I'm still using an old instrument that gives me the opportunity to study what galaxies in these environments are made of. So I use spectroscopy to have the full information about the galaxies. But in order to understand how they look like and have other kind of information, I also use Hubble Space Telescope. And this can provide me not the big picture about the galaxies, but a very good understanding of how things going on.
And I mean, when you were using the very large telescope and kind of trying to learn something about those clusters, how far back in time were you actually looking?
So I can go up to 7 billion years ago, so half of the age of the universe. And this is a very important time because it is in the way that the structure of the universe is not well formed and not well, we don't understand quite well the effects on. So we want to understand how how things change between an universe that is starting expanding and evolving and so on to the days that we have today, and when the structure dominates and changes things. So this is half the way.
And we'll definitely talk more about that and how clusters might have looked in the even more distant past. And for now, Matthew Chan. So you're currently a PhD student at Lancaster University, obviously the best university in the world. Everyone knows that. And you're currently exploring machine learning algorithms to find these clusters of galaxies throughout the universe. Now, I understand that this is not necessarily the standard way that people would use to find clusters. So typically, how would someone go about finding a cluster? Do you just go outside, look up, and then start identifying them? Or how would you do that?
Okay, oh, thanks for having me on the talk show. So yeah, there are multiple ways to look for clusters, multiple conventional ways. So you can use color magnitude relations where you, clusters, the galaxies in the clusters are normally redder than they're normally elliptical galaxies, lenticular galaxies. They're normally redder than spiral galaxies. So you can look for a red sequence relation. And then in that, you can see here that you can use like color magnitude diagrams to try to identify this particular slope that which can also look different in different redshifts. So that's one particular way that shows that you can identify clusters in color magnitude space, which is it's quite a kind of a cheap technique where you don't have to require a lot of computational and time to do. But then you could also use X-ray emission. So I think Andra said that clusters contain a large amount of gas, and this gas can emit strongly in the X-ray radiation. So you could use X-ray telescopes to search for these extended diffuse hot gas in surveys. And then you could also use weak gravitational lensing. So we know that clusters contain, the majority of the cluster is made of dark matter. So basically the light gets stretched and sheared around the cluster. So you could see like in that diagram there, you can see the light, you could get like a density profile from a mass density profile from how much the light is like stretched and sheared. And then finally, you could use like the Sunyaev-Zeldovich effect, where photons from the CMB, the cosmic microwave background, so when they interact with the hot gas in the cluster, they essentially get scattered, and then basically it leaves kind of a shadow on the CMB itself, where you know that okay, this probably is a cluster there.
And so essentially, there's different ways to define these clusters, and I guess some of them are a little bit more technical and complicated than others, like taking an image and seeing where there's a lot of galaxies. But why would you want the computer to do the work for you? I mean, I can understand the appeal that you could just press a button and go to the beach, but is there another reason for it?
Okay, well, in modern astronomy, the data is definitely rapidly growing in size and complexity. So I think it's good to develop like data-driven like tools that can be used alongside theoretical like models as well. So I say if you can to rapidly like process large data sets and to extract information from the data sets, I'd say you probably would start to use like machine learning algorithms to try to identify, let's say in my case, clusters from images, thousands of images, and you could process them very quickly.
So right now we're seeing, I mean, this is not live, but I guess you could run it live. Your machine learning technique working and finding these clusters. How well is it working? And how many clusters have you found with this?
So right now it's in a bit of a proof of concept stage. So in this case, I'm just seeing if the technique works. So okay, in this case, I'm applying something called a convolutional neural network to images taken by the Sloan Digital Sky Survey. And then we just want to see, okay, for this particular, let's say, redshift range, can we try to detect clusters? So this isn't a definite way to say, okay, there is going to be a cluster there, but it's a way to say, okay, we can get like initial guesses of where clusters could be, and then we could follow up on those detections. And
currently, what are the major challenges or limitations? Is the computer already better than you at doing this? Or are we safe and we are not going to lose our jobs?
I'd say in terms of, let's say, cluster searching, I'd say the limitation is probably on what telescope you have, because if you want to look further back in time, you want to kind of have a bigger telescope, where right now with my models, you can only look back, let's say, a few billion years or so. But future telescopes will allow you to probably look billions of years back into to find, let's say, earlier clusters, which probably is better for cosmological models.
And I guess before we move on, and don't forget, you can ask questions here live on YouTube. We do have at least a couple of questions. And I think maybe the first one might be for Matthew about the color diagram.
Yes, we have a question from YouTube. So what is the color diagram and how can it be used to classify galaxies?
Okay, so color magnitude diagrams are basically when you, let's say you try to you get the photometry of an object, let's say a galaxy, and then you could say, okay, if you look at the magnitude of this object in the particular filter, you can then compare it to against its color, which is essentially one filter, the magnitude in one filter, take away the magnitude in another filter, and then the larger the color basically means it's more red, and negative means it's more bluer. So then you could see that, okay, clusters generally have a more redder population of galaxies. So you can see there's a slope there, like which kind of tells you, okay, there's most likely a cluster there.
And I guess another question we have is about what's going to happen to the Milky Way once it stops socially distancing, I guess.
Yes, so the other question is, will the Milky Way also end up in a galaxy cluster?
Andra or Anna, do you want to address that?
Yeah, I can. We actually are in a very, very small galaxy cluster. While we might be moving away from Andromeda, we are actually, if you look, if we were able to get outside of the Milky Way and look from the outside, we would see that there are other galaxies around there. We're actually all flying around each other. So we're actually in a very small galaxy cluster.
So yes, apparently we're more social than we thought. And another question to do with machine learning and our fears.
Yes, so another question is, if we make the machine learning so efficient, aren't we putting ourselves out of a job?
Okay, so I'd say if machine learning was that good, you could literally do everything with machine learning and you wouldn't need anybody. But I'd say you kind of need to be kind of careful, because when we do machine learning, we have to train algorithms. So let's say if we want to train an algorithm to do classification, we have to try to carefully select features, and then we need to prepare, tune each algorithm has like hyperparameters that we need to tune that make it effective. Otherwise, if you just give data to the algorithm, it'll probably end up with not very good predictions.
So far we're safe, but you never know. Skynet's coming.
If I may actually add something,
yeah.
I think machine learning is really good for automating a lot of things that we have to do, like very repetitive tasks. But whenever the scientific process is a very creative process, understanding what actually happens requires human creativity. So I think in the long run, it'll be very difficult for a machine to actually replace humans from that perspective.
But yeah, I guess you could train them to be specialized in a particular area, let's say classifying clusters in images. I don't think you could probably use it for anything else other than that.
And I guess before we go to more YouTube questions, when we have it, I'd like to go back to Andra and talking a little bit more about merging clusters and clusters in general. So you already mentioned a little bit about using kind of different frequencies or colors. So why exactly do we need to do that? What can we learn?
Yeah, it's an excellent question. I am what we would call a multi-wavelength astronomer. I like using very different techniques because they tell us different things. As Matthew was saying, if you use X-ray observations, for example, what shines really brightly is all of this hot gas that's actually right behind me. It's all in this image here is, for example, all of this purple, pink, is all of this hot gas that's located in between the galaxies. Now, if you look in the optical, you can pick up all of the galaxies and some of these black holes at their center. Whereas if you go to radio observations, you can start seeing all of this turbulence and all of the shock waves. So they shine brightly in the radio. So up until now, I have to say, I probably used everything from X-ray, submillimeter observations, far infrared, optical and X-ray observations. So that's something I'm really proud of. I'm, ticking all of the boxes of the techniques. And I think it really tells you something extra when you combine all of the techniques together.
And is there a wavelength you haven't used yet?
I haven't really used like UV, so things that are with wavelengths shorter than the visible, but I think I've pretty much covered almost everything else.
It's good. Very well done. So specifically on X-ray, say, so you can take an X-ray of clusters, and what kind of things do people learn from it? So we've learned from Matthew that we can use them to find clusters. Mm-hmm. Surely we can do more than just use them to find them, right?
Yeah, so depending on the depth of your X-ray observations, there's a lot of rich information. So for example, you can measure the structure of the cluster. So for example, this cluster behind me, you see it's not like a simple spherical ball. It has a lot of substructure that's traced by all of these contour lines. And this tells us, for example, whether the cluster is undergoing one of these massive collisions with another cluster, or whether it's, a relaxed object that hasn't had any much activity or interaction with other galaxy clusters in the recent past. You can also measure, for example, the temperature and the temperature structure of these objects. And this can tell you something about, for example, where, the hot spots in the cluster and what happens then to galaxies if they pass through them. And you can actually also look for very small scale discontinuities that tell you, for example, where the location of the shock wave is. Which you can then correlate with the radio observations.
So talking about radio, I guess you can literally tuning. And what kind of tunes are playing in these clusters? What can you learn from them?
From the radio observations?
Yes, yeah.
So specifically, radio observations tell us about very energetic electrons. So these are electrons that are moving at very, very fast speeds, maybe 10% of the speed of light. And they usually are so fast moving because they've been accelerated by a process such as a shock or turbulence. So whenever you take a radio image of a cluster, you tend to find all of these shock waves. So in this image that you're showing right now, there's this big structure in the north that looks like a toothbrush. And this is effectively a very massive shock waves. But there are also other smaller points in the image. And these are actually coming from galaxies and actually specifically from the core of the galaxy, where some of them have a black hole that is very active and it's effectively spewing out very fast electrons that then we can detect with our radio observations.
And so the other question that people might have is, what's up with these names of like toothbrushes and sausages? Is this something common in the field?
Not necessarily. So we do have a way of classifying, but it's a very dry way of classifying objects. The problem is, of course, when you have, thousands, hundreds, maybe of thousands of galaxy clusters, you tend to give them names like IAU J2256. So you kind of encode the position, the coordinate of the galaxy cluster in its name. But when you have a really exciting object, you don't want to refer to it by its telephone number. So it's much nicer, much like as a person, to actually call it by a name. So it's more recognizable. So hence, because of some of the features they have specifically in the radio, these massive arcs that are tracing shocks, this is why we named them the toothbrush and the sausage, because we thought they kind of looked similar to a sausage and a toothbrush. And people tend to remember them by that. It makes for a very funny pun when you give a talk during like a lunchtime. Much like it is actually for me right now. It's lunchtime. It's 1 p.m. here in the US.
And it's always sausage first, toothbrush afterwards, I guess.
Yes.
So I think we do have also a related question to do with these shock waves about the speed.
Yeah. So maybe the voice from Björn wants to.
Yes. Yes. So Andra mentioned the cluster movement. What is known about the speed?
Yeah, so this is actually an excellent question. In astronomy, we unfortunately only have like a single snapshot of the objects, like taking a photograph. We don't have a video to know exactly what happened, but we can use some of the techniques we have in all of this observational data and modeling and simulations to try to figure out what has happened to the cluster and how fast things are moving. So in some of these very massive structures, much like the one that I'm showing behind me, you can expect the two subclusters that have merged to form this massive merging cluster to move towards each other with speeds of about 2,500 kilometers per second, but some of the fastest ones can go up to 10,000 kilometers per second. So this is, I don't know how many orders of magnitude faster than the fastest person on Earth.
And I guess that also addresses Jorrit's question about what's the fastest shock in a galaxy cluster. Is it then what did you say? Is it 10,000?
So we think that some of the subclusters are moving towards each other at speeds of about 10,000 kilometers per second, but some of the ones that I work with that are very fast tend to be about 2,500. And this is still pretty fast, right?
I would say it's pretty fast for a shockwave. So before we move on to another question about cluster categories, Anna, we already talked a little bit about going back in time. Can you give people an idea of how far back in time we can go and still find galaxy clusters, roughly?
Ooh, that is a good question, because if you go to several astronomers, probably they are saying that what is a galaxy cluster? Do you still have galaxy clusters across cosmic time every time? So these well-known structures, these well-known cities where you can really understand gravity pushing things and have an effect on galaxies. You can go back in time to the first, after the first 5-6 billion years of the universe. So in redshift, more or less up to redshift 1.5. But of course, we have structures that we don't precisely call them clusters, but they are something that are becoming clusters. And we call it, because we are not very original in astronomy, protoclusters. In the beginning of the universe, so when we have after formation stars, galaxies, and then tend to interact with each other, we starting having these structures, and you can see them in very back in time, like after the first gigayear to gigayears of the universe. So you can really go really back in time, but if you really want to call them clusters, and don't make any mistake to any astronomer in the world, in majority are fine. So after the 5 gigayears of the universe.
And so I guess, so if we go back 5-6 billion years, we'll definitely see them for sure, and even a little bit more. But yeah, how have these clusters changed across cosmic time, also based on what you found? Are they always made of these elliptical, roundish, boring galaxies, or in the past they were different?
So they are like humans in a sense. They say you get mature with time, right? You grow up. And when you grow up, things are changing in us, our face, our weight, our everything. So yeah, back in time, they are not completely so mature. So the gravity and the force that they have in galaxies is not always the same. So it cannot completely change the appearance and what's happening in galaxies. It's starting doing something, but it's not completely clear if it's only the environment that are shaping the galaxies, as you have also other factors that may change. But from 7 gigayears ago up to now, they are getting more mature and making a really effect on the appearance of the galaxies. So it depends how back you are looking in time and how well your structure are well or not defined.
And for example, for a galaxy that has not lived in a cluster, would you recommend the cluster experience? Would you recommend the galaxy to migrate inwards? Does it bring any advantages?
No, I don't recommend it at all. So living in clusters is very, very difficult, and the consequences are very, very bad for the galaxy. So no, this is not a very good experience.
And can they ever get out? I mean, can we get like a cluster exit?
Like a Brexit, but galaxy in clusters. So it is rare, it's super rare, but it can happen because when a galaxy enters in the cluster, it will interact with other galaxies, in particular the bigger galaxy that we have in the cluster. And independent of the interactions, because there are several interactions that galaxy will have, it can increase the speed at a certain point and making it goes away from the cluster. So it's not completely a common thing, but it may happen.
It's definitely not easy. So if you're a galaxy and watching, do not go near a cluster. I guess that's the main message. Now, Matthew, and coming back to kind of the need to develop and test machine learning algorithms, are there like new surveys coming up that will allow you to discover so many clusters that you would be overwhelmed?
Yeah, so currently I think the Sloan Digital Sky Survey is a good example of why we need more more wide field surveys, because it looks over like I think overall it looks over 14,000 square degrees of the sky, and the only thing is that it doesn't go to as high as depth as probably upcoming surveys like the Legacy Survey of Space and Time, which will look over probably 20,000 square degrees, and it'll look much more deeper than the Sloan Digital Sky Survey, where we can expect to find more things earlier back in time.
And how much data? I mean, sometimes people do want to know and compare it with, I don't know, how much data they have in their phones or disks. How much data will these surveys be generating? Specifically the one you were mentioning, kind of all sky.
Okay, so the Sloan Digital Sky Survey, I think, has about 200 terabytes worth of data in general, in total. But then let's say if you compare it to the Legacy Survey of Space and Time, you're probably up to 200 petabytes of data in total. So the amount of data that you get is much, much more than currently.
And so you think the algorithms you're testing, would they be able right now to cope with such sheer volume?
I think obviously we'll have to test it first and see how well it actually performs. But in terms of how well it will do in the large quantities, I'd say, because machine learning algorithms can be parallelized, so we can run batches of data at once. So I'd say, yeah, it's possible to, because we can go straight from raw data to output. So we don't have to make assumptions and stuff to classify stuff and predict things.
And do you have any idea, I mean, based on our current knowledge and I guess how deep that survey will be, how many clusters we expect to be able to find? Do you have like a rough estimate?
I'd say in the Sloan Digital Sky Survey, we could probably get up to maybe thousands of clusters. But I think but for LSST, you probably even get hundreds of thousands of clusters, just because you can see much deeper into back in time.
So definitely a lot of things to be discovered and studied. And before we move on, I think we do have a question from YouTube about cluster categories.
Yes. So are there cluster categories or not really?
Andrew, I'm not sure if you want to comment on how astronomers, even though we don't really have a definition, a very good definition of what the cluster is, we probably still group them, right?
Yes, for sure. We like adding labels. I'm not entirely sure that's a good thing to do. But indeed, specifically looking at kind of more mature, evolved clusters that we can find in our neighborhood, in the local universe, we do tend to see that they tend to split in two categories. Some of them are pretty isolated. They have all of this X-ray emission. The hot gas has a pretty spherical look to it. Most of the galaxies inside are what Anna was calling, these kind of spherical, very old galaxies that don't have much active star formation. And these we call relaxed clusters. So these we think are clusters that haven't interacted with the cosmic web or with other galaxy clusters in, let's say, in maybe like 2 to 3 billion years. So this is a very nice example that David is showing right now, where you see all of these very red galaxies that are typical for a relaxed cluster. However, we very recently realized that 50% of the galaxy clusters, even close to us in the neighborhood of the Milky Way, are actually undergoing these collisions. So these are clusters that are clearly actively in a phase of growth, of formation. And yeah, so it seems to be, at least in the local universe, to be 50-50 split. And then of course, the more we go into the early universe, the more of these merging, colliding clusters we find, but all of them tend to be lower mass.
And so if we have, I guess, clusters keep merging, is this just going to be continuing forever? Will they just keep getting bigger and bigger?
That is an excellent question, and I think I do not know 100% what the answer is. So we would expect, as clusters are near other clusters in the cosmic web, that they would, as it has happened for the last 10 billion years, be attracted to each other through the mutual gravity and grow into bigger and bigger clusters. However, the universe as a whole is expanding, so things are moving away from each other as well. So it's kind of a game of tug of war, where the galaxy, the gravity between the galaxy clusters is pulling them together, but the universe as a whole, the fabric of space-time, is stretching, so they move away from each other. So I don't know, my bet is that they will still keep growing, but there are people that would disagree with me.
I guess at some point there is a limit, into things you can merge into. And I know one thing that people may want to know. So we've talked about how fast these shock waves can travel, but galaxies and galaxy clusters are also moving quite fast.
Yes.
Do you have an idea of how quickly they're typically moving in a cluster?
So you can imagine something traveling at 800 to 1000 kilometers per second. So very fast.
So they're definitely speeding. And does this make it like quite awkward when they merge, or because they're going really fast? That's quite quite an accident waiting to happen. Or are they moving so fast that it's very hard for them to hit each other?
No, inside the cluster, it can, the velocity, they hit each other and it strips out completely the gas and even stars and everything else. So at the same time, it can pull the galaxy away from the cluster, the smaller one. So the speed is very important to really understand what's going on in the cluster and how it can change a galaxy inside the cluster.
So while we don't have more questions from YouTube, I do have a few questions so we can know you all a little bit better, right? So because we're talking about galaxy clusters, I think my first question has to be, what is your favorite galaxy cluster? And I suspect that, well, Andra has some background that might suggest something, but is that your favorite cluster, Andra?
I think my favorite cluster is the one that I'm working on right now. This is a cluster that I work with one of my students, Joe Cairns, last year. So it used to, Antlia used to be my favorite cluster last year. Now I have a group of them. I'm working on about 20 of them. So they're all like, I love them equally.
Very nice answer. Anna, do you have a favorite galaxy cluster?
Yes, I have one, and maybe the fault is from Andra. I really love El Gordo, and El Gordo is my biggest frustration ever because I'm trying to get HST data to really understand it better. Because it's not a completely relaxed cluster, so it's not completely post-merged. That is, and it is half of the way of the age of the universe, so 7 billion years ago. And there is a lot of things to going on, and it can help us to peer into the past to understand galaxy formation and evolution. So there is a lot of things that I would like to learn from with that cluster and from that cluster. So yeah, I think this is my favorite object in galaxy clusters.
Algorithm. Matthew, what is your favorite galaxy cluster?
Allow me to show you.
This is called,
so this is called, I'd say it's called the smiling cluster.
Smiling cluster.
But this is just because the clusters happen to be in the right place where the light from galaxies behind it stretch so this smiley face that you see is a stretched a lensed galaxy that's behind the cluster. So I think the Daily Mail called this the happiest place in the universe.
I mean, I'm afraid to say that they're wrong because inside the cluster, it's definitely not happy, right? It's anti-ecstasy, so I don't know. They might be wrong. The other thing that I was going to ask you all, and especially thinking about the role and like the importance of role models and astronomers that might be inspiring for you all. What is your favorite astronomer? And I'll start with you, Matthew. Do you have like a favorite astronomer, either alive? I mean, it could be a supervisor, obviously, best astronomer ever, or someone long gone?
I'd say probably an astronomer called George Abel. I'd say he's a pioneering astronomer for clusters because he created probably the first cluster catalog, where he did all his where he used photographic plates and then he did all his calculations by hand to try and find the clusters in these photographic plates. And he spent many years looking for these clusters to make his catalog.
Do you think he would be happy if you show him the machine learning algorithm that can do it in a few seconds?
He'd probably love to speed up the process. Yeah.
Anna, what do you have a favorite astronomer?
Favorite. I don't say favorite, but I have someone that I like to hear about, and I like the papers and motivate me to study astrophysics, which is Vera Hogan. First of all, she's a woman, so she was the strength that I can fit in this field, and she studied the spiral galaxies in order to, and she understands that it's something that could be dark matter that may exist to explain the orbit of stars around the galaxy. So since I'm completely passionate about to understand the form or the shape and evolution of our galaxy, it implies to understand as well the environment where galaxies reside in. So yeah, I think she is my favorite astronomer because she makes me think about stuff and peer more in the past and in the questions that I want to see answered.
And Andra?
I don't think I have necessarily a particular person. I think I've had so many mentors that inspire me, but particularly when I was growing up, I grew up in Romania and we don't really have much astronomy there. There's no department that does astronomy. So I didn't really have exposure to role models that much. So it was really helpful for me once I actually got into the field to have people that I actually met in person. They were excellent mentors and I look up to all of them.
Really nice. And so talking about, I guess, back in Romania when you were growing up, did you already want to become an astronomer? Was that your childhood dream, or you wanted to be something completely different?
Actually pretty close. So I was not the type of child that wanted to become a doctor or a lawyer. I was like, definitely not those. Ever since I can remember, I wanted to become an astronaut. But that felt very, very difficult to achieve. I would still go to space if I could. And if someone would offer me that opportunity, I think that would be so cool. But I realized, like, you know, the next best thing to going to space is to study it. So that's how I landed in astronomy. But I think I kind of knew I wanted to do astronomy when I was maybe like 10 or 11 years old.
It's yeah, pretty early to know what you want to do. I mean, technically, I guess you're kind of in space, so that has happened. Anna.
So no, I just discovered that I want to be an astronomer when I have 18 years old. So I was too late, and I have a complicated path to go to astronomy. So when I was a child, I want to be a mathematician because I really love math, and I think this is the language of the universe. So it can answer me everything. But I want to apply math to something. I don't know to which or what I want to do, but I really love to use maths in my everyday life. But when I was in ninth grade, I started thinking about economics, and I made a path towards economics, and I went in the faculty to study economics. But there I learned that in order to be a very good economist, I should learn physics, because the market tries to move like it has a gravity. And the market as well tries to understand things like cows and everything else. So I have a lot of very good professors in the faculty of economics that told me, oh, if you really want to understand this, and I have a lot of questions, you should go to physics and mathematics, and you should think to be an astronomer. And they are right. I understand much more now about economics that I was understanding only to purely studying economics. So that's why I went to astronomy and did my path in astronomy.
And Matthew, did you also go through an economics phase, or did you go directly to astronomy?
I would say my inspiration is probably from my environment, because I grew up in the same hometown as Sir Isaac Newton. So, you know, if you live in this area, you see there's a lot of statues, monuments, buildings, schools named after him. And it's just, for someone like Isaac Newton, it's a definite good role model to have because of his work in physics, laws of motion, universal gravitation, telescopes. I'd say, yeah, definitely, as well, I think my most favorite quote of his is, if I have seen further than others, it is by standing upon the shoulders of giants, which definitely makes me think, oh wow, if Isaac Newton could do what he did, maybe I could make my contribution as well in physics.
Sounds good. So before we finish, I wanted to ask you kind of a big question related with your own research. I guess on one hand, what do you think is the most important open question within the clusters field? And specifically one that you would really love to kind of solve or address? And I don't know who wants to go first.
I can go first, since maybe I can scoop the good ones before everyone else. So one direction that I definitely am moving with my research is to understand how clusters form in the early universe, and specifically to figure out when clusters first form, when does this gas between the galaxies, when does it become a thing, and when does this gas actually start to interact with the galaxies, remove the gas from the galaxies, and effectively help them transform from these beautiful spiral galaxies outside of the cluster into these passive red evolved galaxies within the cluster.
And Anna, do you want to go next?
So yeah, one of the questions that I want to solve, and I really want to have not an answer, but better questions in the next 5 years, more or less, is are star formation really killed inside the clusters, or are still stars forming? So when you have a HST program, a Hubble Space Telescope program, to go deep in UV, and you are trying to answer this question. And I really would like to have the opportunity and the money to stay in academia in the next 5 years to really use the data and explore the data and tell the community this information and how, and as well improve our questions and see further. Also, I would like to understand better if galaxies are really changing before or after entering the cluster, and how it changed across cosmic time, because it's not completely clear for me that, for example, the elliptical ones, when you can divide it in volts and disk and things like that, more complicated in shape, really happen inside the clusters, or really in the moment they are trying to cross to enter the cluster. So this kind of things is like a mystery for me, and I would like to have an opportunity to explore these kind of questions, looking a little bit like back in time. And of course, I would like to have more clusters and explore the galaxy evolution, like with gravitational lensings, and have more insights about galaxy formation.
And Matthew, what is the big question you'd love to address?
I'd say, can we show that clusters are good for cosmology? I'd say yes, because you can use them. So for example, you could look at the Halo mass function, where you could compare observations to simulations, where let's say you count the number of clusters of a particular mass as a function of distance. And then you can see, okay, do the number of clusters that we observe at different distances, do they match the cosmological simulations? And hopefully my work might help contribute to that.
I guess you'd be able to provide even like a larger number of clusters at different cosmic times, right?
Yeah, I hope so.
That's good. So good luck to you all to be able to unlock that. And as Anna said, make even better questions, because I think that's really crucial. And I'm sure you've inspired many people to study clusters in its various components, of course. Unfortunately, that's basically all we have time for today. Thank you so much again, Andra, Anna, Matthew, and the voice from beyond. It was really brilliant to have you. So let's have a big round of applause. Also, thanks to everyone that watched and participated and asked questions. So we will be back next week at 5:30 UK time with the amazing Brooke Simmons, Julie Wardlow, and João Calhau, who I think also asked at least one question from Lancaster University, to talk about supermassive black holes and superactive distant galaxies. So it's obviously going to be amazing. Until then, don't forget to subscribe here so you can get the links directly. Also watch previous episodes on our YouTube channel, and you can check out the entire program on xgal.uk. So keep looking up, everyone, and I'll see you next time.
Liftoff of mission 41D, the first flight of the orbiter Discovery, and the shuttle has cleared the tower. Welcome home, Columbia. Beautiful, beautiful.
You want us to take it up for hangar, Joe?
We're going to dust it off first.
3, 2, 1,
0,
and liftoff. Liftoff. Americans return to space as Discovery clears the tower.
Roger roll, Atlantis.